All right, so this is going to be my status report. It's been, I counted, about 70 days since my last update, but this is about 3 days of work, all done in the last 3 days. So I have a very weird duty cycle. So these things are actually useful in terms of like a deadline that forces you to do something. And I picked for the topic of discussion, maybe we should build a robotics operating system. Oops. Okay. So quick recap, then I'll talk about the BeagleBone experiments that I've done on the robot you're seeing. And should talk a little bit about the early fabrication stuff for the Nature is Murder full robot, and then we'll discuss robotics OS. And in case you've forgotten, so the robot with the wires and the blinking board, that's accessory before the fact. It's a very simple rig just to test the compute and software. And the main robot is the one you see next to it. It's like partially assembled, slowly being fabricated. That one's the full 6-wheel rocker bogie thing. Okay, let's see. Okay, so if you remember on August 3rd, the state was that I had finished fabricating the accessory before the fact, except for the wire harness. I had like, the 3D printed parts. I had the servo motors and the drive motors, but I hadn't actually connected up anything. And on the main rover part, I had finished the CAD design. So this is what it looked like. All right, this is what accessory before the fact looks like now. And as you can see, it is a cable management nightmare because there's a shit ton of stuff going on. There's 4 servo motors to control the 4 steering wheels. There's 2 drive motors. The final robot will have 4 drive motors, but this one just has 2. And each has 6 conductors coming out of it. So 2 are the drive positive and negative terminals of the motor itself, and the other 4 are for the quadrature encoders. So that's 6 conductors per drive motor. So that's total of 12, plus 3 each for each of the servo motors. So that's another 12. So 24 cables just for this, plus you've got cables coming from the battery, right? And these are all, by the way, the really tiny JST ZH and SH connectors, which are like 1 millimeter and 1.5 millimeter. So they're really fragile. I had to special order I didn't want to like even try soldering those connectors. So I had to order them from eBay and Amazon. So I got a pack from China and have a bunch more coming. What are some issues still? All right. So right now what you're seeing, it's mostly disconnected except for one side. So the one side's motors are connected with crocodile clips, so they're not yet soldered or connected. The encoder wires, I had them connected, but they're now disconnected. And the reason is I'm only running sample code now, and it's all the sample code is blocking. So if I try to test the motor, the encoder program will stop running. And if I try to run the encoder, the motor program will stop running. And the way I actually tested the motor was to power it from a separate power supply and then test the encoder. Let's see what else. I realized too late something very dumb, that 4 wheels means it's not like uniquely determined. That's why people like tricycles for simple robots. 4 wheels means one is likely to be off the ground. And unfortunately, one of my drive motors is off the ground, so it kind of screws around a little bit. Let's see. Okay, so I was thinking I'll try and do some kind of like simple suspension, but maybe not. I mean, this is just there to test all the rigging and stuff. So even though one of the wheels lacks traction, it'll do the job. So I'm not going to kill myself about it. Let's see. And as you can see, I haven't tried to trim or shorten or route the wires properly. It's all like way too much cable here. But it's not worth solving for this particular rig. All right. So let's see any other. Oh yeah, if you see the 2 drive motors, the 2 motors in front, There's actually not enough clearance in them between them because I didn't correctly anticipate how thick the cables would be for connecting. Let's see if I can show you more closely. I don't know, can you guys see how close the clearance is? Yeah. Yeah, so I don't know if you could see, but the clearance was really small. So I have actually reprinted the chassis and will move the whole assembly over to the new chassis. But right now it's good enough. Like sometimes the wires sort of hit each other when the servos turn, but it's, again, this is like a test rig. It's not a real rig. Let's see, and this is just showing the right drive motors conductors. I haven't even put in the board leads for the left side. So this is like even less complicated than it's finally going to be. All right, let's see. And on the other, the main robot, so not the test rig, I started 3D printing the CAD design. So for those who came in late, yeah, this design, I started printing it. This design, I haven't done any detailed refinement of dimensions and like figuring out whether like things are geometrically sensible. I just like half-assed it, and I'm printing the half-assed as a rough draft just to get a sense of the design, because this is complex enough that I'm going to get enough wrong that there's no point being prematurely precise. It's better to do like a rough print, see the test assembly, how it works. So a couple of things that I've already figured out. So let me move the camera and show you some up-close details. So you can see on the back, I don't know how well you can, let me see if I can move the camera. Yeah, the clearance between the blue thing is just cardboard, and it's supposed to represent the BeagleBone board. And I didn't correctly estimate how high the parts will rise out of it and how much the connectors will jut out on top of the board. So I think the clearance is too low. It's about ½ an inch between the top deck and the board. And just looking at this guy, and the servo motor connectors themselves are more than ½ an inch tall. But luckily, I think I have room here to lower the heights of the standoffs for the board. So I think I can keep the overall height the same and still do it. Let's see, what else can I show you? Oh yeah.
I think you switched the camera because we saw the fan instead of the beagle board.
Oh, I was just pointing it badly. Okay, let's see, what else can I show you? Let's see. I don't know if you can see the, hold on. This is hard to show. Oh yeah, okay, I'm just going to show it to you from the outside. The aluminum is sort of press fit onto the hinge, and I got the tolerances wrong and had to shave it down. But it's partly a dimensions problem, partly I'm printing with PLA, so there's a compliance problem. So I cut a slot to create enough compliance, but only in one of the dimensions. So I have to cut slots in the other dimension so it press fits properly. So a bunch of little issues like that. But the basic assembly came together, so it's not too bad. So let me point it at this guy. Okay. Hold on, let me position it so you guys can see what happens when I.
So is that a beagle board on accessory before the fact?
Yes, that's a BeagleBone blue.
Mm.
Okay, so that was the previous one. That's the Beagle board. This one just has a piece of paper where the Beagle board would go. I just ordered a second one. I was going to like just rip it out of this one and put it in the final rover, but now it's like, it's cheap enough. I'd rather have two boards as a spare anyway, and that way I don't have to take apart the test rig in order to build the main rig. So a little more expensive, but worth it, I think. Okay, so let's move to the main topic for today, which is compute and software. So on August 3rd, if you remember, I gave you guys a brief introduction of the Beagle board. And my progress at that point was I was having driver tower troubles, but I eventually got it figured out. I got it up and running and got to the blinking LED by then. And for those of you who haven't looked into this yet, it's from the BeagleBone family, which is basically kind of like a Raspberry Pi. And there's a version called the BeagleBone Black, which is kind of equivalent to the Raspberry Pi, and it came with a robotics cape. And that cape got integrated into the board itself, and that's how you get the BeagleBoard Blue. So the black plus cape integrated becomes the blue. Okay, so what's my current state? I installed and explored the robotics library. They have a really good one. It's the Debian package librobot control. It's got 11 contributors. It seems to be under like kind of sort of active development. Last release was last July, but it seems to work pretty well. And the original guy who wrote it, it's made by a company called Strawson Design, but I suspect Strawson Design is one guy. So it's like, Yasha, a company of one guy, and he wrote the library for basic robotics, but he's done most of the basic stuff. It's under MIT license. So as we do more code stuff, we should start thinking about licensing, by the way. Anyway, so tests passed. I did a bunch of stuff. So I didn't write any code. I just ran sample code. So don't give me too much credit for this, but I give myself some credit for even getting sample code running. So let me show you how that works. Let's move over to my, all right. Can you guys see my IDE screen? It's Cloud9. Okay, I don't know how well you can read it, but Cloud9 is the AWS IDE, and it's an alternative to SSHing, and it has some conveniences. Okay, so let's run the hardest test first. And if my cables hold together, okay. So those are the parameters for the testing motors routine. So let's try to do okay, minus, sorry, this is very slow to respond. Let's do, I think it's motor number 1. And let's just sweep it back and forth. Oops, it's very slow, sorry. Can you see the robot moving? Yes.
Trying to.
Yeah, so it's sending a sweep signal. So it's just moving the wheel back and forth very little bit. I don't want to do too much. Let's maybe, I can try maybe moving it a little bit more aggressively.
Why do you select a motor with a -M1?
So there's
Apparently, if you don't select a motor,
there's 4 motor outputs. So the motor that I have connected up is connected to output 1. That's all that is.
okay. I know,
Yeah.
just from the documentation, it seems that if you don't specify a motor, it will send the same command to all motors.
Yeah, so I just didn't want to turn on all of them. Yeah, so now you can see it's moving a little bit more aggressively. All right, what else? Okay, let's test the servos. This time I will use the option that you pointed out, Eric, which is since all 4 servos are connected up, let's make all of them do something. All right, let's see. Oh, I'll point out one thing once we see if we can actually get it to work. I'll do the same sweep thing. Can you see the steering motors turning?
Yeah.
So all of them are turning.
Can you do it both at the same time, the steering and moving?
No, not yet, because the sample code, if I start one, it'll kill the other one. It's got some sort of like process priority thing where the moment you start another one, it'll kill it. So I basically have to write new code that combines the two. Let's see, what else can I show you? Oh yeah, it's got 9-axis IMU on board.
Do you have Dead Reckoning integration software, just measurement?
I haven't looked into the sample code, but I don't think it's got integration software in the library. So I'd have to integrate myself. So yeah, you can see it's got XYZ acceleration, linear and rotational, and it's got magnetic field. So my first idea for navigation is actually going to be magnetometer reckoning, and it's got a temperature sensor. Let me see if I can do some. I'm just going to move the thing around, and you can see that the numbers move. And my battery fell out. So you can see the numbers move. I don't know how accurate they are, how well calibrated they are, but it seems to work. Oops. All right, let's see what other routines I could quickly run. Oops. So all this is C code, by the way. There is a limited Python library, but it doesn't look great. The encoders I'll show you on my Twitter stream. I think it has a barometer as well. I haven't actually tried that, I think. Oh yeah, it reads temperature, pressure, altitude filtered. All right, nice. It had me calibrate the magnetometer by rotating around like you do on your phone to make the compass work. So, yep. All right. So I think that's good enough.
A quick question about Cloud9. So Cloud9 is IDE loaded in your browser, and it connects to your local network to connect to the board through SSH.
Yeah, I don't know that it's SSH. It goes over port 3000. So it's, I think, running a web server, and then a SSH is tunneling through the web server, something like that is happening. All right, I'm going to unplug my power here. Okay, and it's got some other stuff like, let me put since my demo part went well. That was the main thing I was worried about for today, that the demo part should go. Now I can put the camera back in its normal position. And so a bunch of problems going on, like I haven't calibrated the servos, so their 0 positions are all over the place. Like I thought I mechanically put them in the right place, but when I actually send all the servos to 0, the 4 wheels are pointing in completely different directions. So I now have to like unscrew the horns and like reset them, or write code that'll offset by the 0 error and so forth. Let's see.
Is that every time you turn it on, you have to reset it again, or it remembers?
I think it's static. There's a static 0 error basically. So, all right. Anurag, you joined just late enough to miss my Hello World demo with the robot moving around. But let me.
Your successful demo.
Successful. So you'll have to take Eric's and Myers' words for it that it worked. But in case you probably used this since you seem to know all about various IDEs. But yeah, I was using the Cloud9 IDE to run the computer, run the robot.
So Cloud9 is from the BeagleBoard guys, right?
No, it's from AWS. So AWS uses it for AWS, but they've open sourced it. So the BeagleBoard guys use it as their. You can also SSH in. I prefer this because it's quicker and works right in the browser. All right, where were we? Okay. So I showed you guys a Blink. I showed you last time, but I showed you the IMU. drive motor control, servo motor control. Encoder is the one thing I haven't shown you because the wiring is not set up for that, but I'll show that to you on the Twitter feed. Can you guys see the encoder stuff? Yeah, so this was basically, I rigged up the motor directly from a power supply and had the encoder turned on. That's all it is. And to actually run the motor off the board and the encoder off the board, I have to write new code, like I said, because the code samples kind of block each other. So I can't use the sample code for that. But okay, so that's my status here.
So that RC test sensor is a Python script, C program. What is it?
C, it's all C.
Okay.
Let's actually go over and quickly look at the code. So the GitHub repo and documentation. Okay, so they have a pretty good documentation. They have a manual. So the basic stuff is a bunch of API modules. So there's a whole bunch of function calls. All of it is C. Let's see. And it's got pretty well commented code. Let's actually go to some examples. So these are the examples I was running. So let me pull up the example. Yeah, RC test motors. This is what I was running earlier. So as you can see, it's pretty straightforward C code, though I haven't written C in like 25 years. So this is all like making my eyes glaze over. So I have to like really refresh my mind on how C works. But it seems close enough to MATLAB and Arduino's version of C that I hope I can get up to speed quickly. Yeah. So this is all the test scripts. And the one other thing I want to show you guys is, let's see. Yeah, they have a project template. So this is going to be my starting point. It's got a make file and let's see, where's the actual, okay, yeah. So it's got a bunch of like stubbed out bits, but it's basically a single loop standard kind of thing. You run everything within that single loop, and there's a safe exit module. So you hold the pause button down for more than 3 seconds, the board will like stop whatever it's doing and exit. So that's the basic architecture. And within this, you have to decide what code to shove in. And I'm guessing I'm going to have to like probably work in C because their Python stuff doesn't look that great. Let's see. I have a link to the Python stuff here. This is, by the way, on my own ROM. It's not on the collective ROM, but I'll move it over once I have it cleaned up. So I haven't looked at this repo much, but this is the Python repo. So this seems to do some stuff, but I think the C code is a lot more comprehensive and full-featured. But overall, I'm really pleased with this librobot control library. It's well documented. It's got like almost all the basics, motors, sensors. It's written for the BeagleBone, so don't have to like do weird porting from our Raspberry Pi or something. So I'm hoping this means I can move relatively fast. All right, let's see. Okay, so that's it for, is there anything else I wanted to show here? Yeah, it's a reasonably active Git project, like I said, good documentation. Yeah, and BeagleBone runs ROS, though the onboard SSG or eMMC is not big enough to hold ROS. It's got, I think, 4 GB. So the instructions I saw recommended basically adding a micro SD card to run ROS if you wanted to run ROS. And I imagine if I wanted to do things like VNCs and containers and things like that, it would probably run off the SD card. The onboard SSD is much more reliable, but it's very limited. So I'm sort of now thinking through what I can use it for. Right, let's go back to the presentation. Let's go back to present mode. All right, anything else I want to talk? Oh, so terminology to be aware of. BeagleBoard calls it a cape, but it's the same thing as a Raspberry Pi hat or an Arduino shield. Okay, so that's it. All right, so my next steps for the main development path. So I have a client, Jim Keller, actually, who we've talked about before, the famous chip guy. So he likes to talk of ambitious engineering projects in terms of like crawl, walk, run stages. And I decided this is like so rudimentary. I had to add a flail stage. So my test rig is currently at the flailing stage. I hope to get to crawl very soon, which would be basic code to run, CAN trajectories, no feedback, except maybe on the magnetometer heading. Walk would be where you're talking about, Meyer, which is take the dead reckoning accelerometer and gyroscope inputs, double integrate them, and produce like, I think it'll be a high drift, very noisy position estimate. But you can also sort of triangulate a little bit. So that's kind of an interesting thing. Like, since we have encoders on the motors, if you integrate that, you'll get a path arc length estimate, and then you can triangulate that versus the absolute space integration from the dead reckoning. And hopefully that might give you more accurate dead reckoning. The run stage, I'm hoping to add some sort of sensor. So probably ultrasonic, like some of you are using, or maybe even as simple as Whisker, and some extremely simple route around algo, like, back up, turn right 30 degrees, try again, and keep trying until you go around the obstacle, and then try to head back to the main heading. And dances, where hopefully it'll get to something that looks like a real robot. Like, it has a map, it can do a little bit of slam, it can actually plan a path on a map, something like that. So that's all on the main development path. But there's a bunch of housekeeping stuff which is really not in my wheelhouse, but I have to learn, I guess, all the computer stuff. So very basic stuff. I'm sort of poking around and wondering what's the best practice. Like, the BeagleBoard has 2 user accounts. It's got a root account and it has an account called Debian. And as I recall, best practice with Unix systems is to do all your work in like a regular account, and then only switch to super user mode to do like critical things for safety. But all robotics code has to run as root because it's doing very low systems level stuff, I think. But yeah, that kind of.
I'm sorry, is that a requirement of the library that you run as root?
The library, I think everything runs as root. But yeah, maybe some things don't need to, but I'm assuming in general, many things will need to run as root because so many basic functions are being controlled. But yeah, that's something to think about. Something like as simple as how do you even deploy code? Like, this has so little memory, and the connectivity is so weird that should I be copying files over, or should I be like running Git on the board itself? Or should I actually be editing code directly on the board?
Do you have internet connection?
Yeah.
Wi-Fi?
The board can talk to the internet.
So Git is the best solution. You run Git and it pulls your new whatever from wherever.
Yeah.
But do you compile it on the board itself?
Yeah, I'd have to compile it on the board because there's no emulator environment, and I can do source editing on my laptop because it's faster. But other than that, everything has to happen on the board.
Well, you could cross-compile it for the BeagleBoard chip and then copy just the executable, that is, or the binary.
That's probably above my skill level. I probably have to set up something like an environment that emulates the BeagleBoard environment. Or something,
No. You just have to set the compiler. So cross-compiling is like you compile it on some other board than on the one in which you run the executable. For example, you can compile something on x86 for the ARM board and then just copy the executable. So you just need a compiler.
So that'll work for most of the code logic that stays on the board, but any code logic that affects hardware and sensors and actuators, there's really no way to test the compilation except on the board, right? Unless you're emulating motors and things.
Just a second. Let's talk about the process. You write it on the laptop, and what Anuraj is saying, you compile it on your laptop, then you pull it to the board and test it. But compiling is a heavy activity.
Oh, okay.
And you don't want to do it on the board. So how big is the disk on the board?
It's 4 GB, so it's actually pretty capable.
There's a RAM.
The disk is 4 GB. The RAM is 512 MB, I think.
Oh, that's very little.
Yeah, I don't have very good intuitions for how much GCC takes or something. Let's see here. Hold on. You can quickly.
Yes, small
go to
programs
the
could be compiled. It should not be like the ones you are running. I don't think that should be a problem to compile it on the board
Yeah,
itself.
I think my code will be extremely small and light. So hopefully I should be able to just compile it on the board. But if not, yeah, I'll have to do this
So,
transpiling thing you guys are talking about. So
so
I
does a
mean,
bigger board have an operating system
it's a Debian Linux.
in 4 GB?
Yeah. It's running a very, it's less capable than an RPi, but definitely more capable than like an Arduino or something. So, okay, so I'll figure all that out.
Add an SD card, is that right? If you
Yeah,
wanted
you
more?
can add an
Or it
SD
has an SD card.
No, the main, so it has a eMMC, so I guess that's a slightly less capable SSD. So with like poor response or whatever, but it's like more reliable than an SD card. So that's 4 GB on board on the board. It also has a micro SD card reader, and there, of course, you can put in as much as you like, and you can boot from the micro SD card, and yeah, but you still wouldn't have more memory. So the memory will be the bottleneck for compilation and heavy stuff. Let's see. Okay, so all that I'll figure out. Okay, so that was my status report. Any questions or suggestions or feedback on the status report before we move to our discussion of the day? Any questions about BeagleBoard? If you want, we can explore the documentation and stuff a little.
Well, the BeagleBoard seems to have more built-in sensors than the Raspberry Pi. Okay,
yeah.
So I'm wondering how you're planning to take advantage of it. You told us basically in the walk stage, in the run stage, you're going to do some sort of integration. But do you have any earlier milestone in mind to check out if these sensors are interesting or useful or whatever?
I guess I'll just do some basic tests, but I'm like at the, like I said, flailing stage where I have to do basic things like get the motors and servos running. So that's actually, it's not just that it has a lot of onboard sensors. It has 4 edge bridges that can drive up to 1.5 amps. It's got 8 servos right on board, so you don't need a cape for all that. So all that is an advantage. It lowers the form factor. So the height of the robots can be like about an inch shorter because you're not adding hardware on top, right?
Yeah.
So yeah, at the flail stage, I'll definitely be just figuring out these basics. Where am I? Yeah. I'm still worrying about like calibrating the servos and making sure all the zeros are pointed in the right direction kind of stuff. So once I get past that, extremely basic location awareness and movement awareness, and then we'll talk, all right, can I do something interesting with the temperature sensor? For example, if a part of my room is sunlit and at a hotter temperature, can I write a simple code that goes away from hot parts to cold parts, right? So you can do very simple things like that. So temperature, pressure, I think are interesting. Magnetometer would be good for basic navigation, but unless you're outdoors, it doesn't actually add much. Like going north, I mean, in my apartment, it'll go in some random direction. Let's see this. What else is interesting?
You use a magnetometer in order to help you integrate the accelerometer and gyroscope data. Because
yeah, that was some sensor fusion I was planning to do. Yeah.
No, it gives you an absolute heading rather than a change in heading.
Yeah. So that's on my, I guess, walk stage. So after crawl, so there's 3 sources of position intelligence. You've got dead reckoning with the IMU, you've got magnetometer, and you've got encoders on the motors. So all 3 together might hopefully give you a relatively low noise location signal. But I think at some point you will need external referencing with a camera signal or like, landmarks or something, because all this will have heavy drift problems.
I have a comment on the flail and walk stage. It's like if you could figure out how to use the Python library, it will actually solve a lot of time for you in terms of like compiling and handling C errors and stuff like that. Like, and if you can use VS Code, VS Code has this very good thing called VS Code Remote, which is more or less like what you have now shown in that BeagleBones Cloud ID type of thing, where you can basically you will connect to the interpreter running on the board, and you will get the whatever autocomplete and everything from the libraries installed in the board. So your interaction would be more real time, and the UI would be running in your desktop or laptop, and whatever autocomplete and the environment would be there. It's similar to what you have shown now. So
okay, yeah, I definitely should check it out in that case. Yeah.
Yeah, it will cut your iteration process because you don't have the compile step there, and it will be very, and you don't have to handle all the C's memory errors and other things, and yeah, it would be more.
I'll definitely check out the Python code, and my impression is that it's like, and a much less full feature than the C code. So depending on the trade-off between having to write new code versus use difficult old code, it's going to be one or the other. But I do want to actually try and make sure I learn how to use both the C and Python code, just to get a little bit experience with both and see how it works. Especially because so much of what you guys are doing is various kinds of Python things, right? So if you want to like interoperate, it would be nice to have both. Okay, so I'll be flailing, crawling, walking. So hopefully by December, I'll get to at least very rudimentary crawling, like maybe give it one command, like go forward 10 inches and go back 10 inches kind of stuff. We'll see if I can get there.
Python and C know how to talk to each other. So theoretically, I mean, if you take my Python, which connects to Discord, you could run that on your Beagle board, and the commands that it's executing would be written in C instead of written in Python. So it's not that difficult. I mean, your Beagle board definitely runs Python. It's just the low-level functions, maybe you don't have a good library.
Yep. It does run Python, and I haven't, like I said, this is a very rudimentary sense. I have just glanced at the Python library. It just seemed to have fewer files than the C library. So that's my basis for saying it's weaker than the C library, but maybe they've written very big Python files that do a lot more or something like that. All right, let's
did you try anything with the PRUs on board?
I'm not literate in that level of abstraction yet. I'm just basically doing whatever the shell or basic Linux environment allows. But yeah, some of the stuff, some of this is sort of transparently handled. For some reason, I think 3 of the quadrature encoders are handled distinctly, but the 4th one is handled by one of the PRUs for some reason. So it's like it does a bunch of like automated, I don't know, load management, I guess. Some things go to the PRU, some things go to the main processing. So I haven't yet figured all that out. I have to invest.
So the library handles the load.
Library handles, uses both resources as far as I know, but I don't know how it does that. So like I said, I'm not literate at that level of abstraction.
And I have a general doubt in terms of encoders. Like my JetBot thing doesn't have any wheel encoders or any of the sensors you had mentioned. It just has the monocular camera. That's it. That's the sensor. You mentioned drift problems, right? In finding the reckoning or the position information of the robot. Would a camera itself suffice, or like would these be finally integrated with the camera, like the encoders and other things, the information from the encoders?
So I think the big trade-off there is that these other sensors are extremely lightweight and very undemanding in terms of computational processing. Whereas video processing, even though it's much more powerful, well, you have to process video. You have to recognize what you're seeing. You have to segment images. You have to recognize landmarks. You have to triangulate. So you can use video, obviously, and humans do that all the time. But the equivalent of encoders, I guess, is like our ear canals or something. It's much worse, but it's also much cheaper. And I think the most common way to use both is you use all the more primitive sensors for like fast real-time control and navigation, especially real-time control loops where you have to respond in like, millisecond or whatever, not millisecond, maybe 10th of a second or something. And occasionally you will sort of correct drift errors using vision references. So you might say, all right, after every 10 minutes, check with your landmarks and zero out the errors. So that's one way I've seen people do it.
Okay.
Yeah, without encoders, generally in SLAM, you face the loop closure problems. Loop closure is like when you return to the same place, you are not having these same coordinates on your map you created. So without
Would it be
encoders,
easy to install an encoder in my thing? I have no clue about hardware. So just my wheels are just the normal wheels. Should I get a new one or something?
So you'll have to show us photos of your wheels, because depending on how much room there is and whether there's like a space in the axle to generate. Yeah, you should be able to install one on that. So,
Okay.
So the type of encoder I'm using is called a Hall effect sensor that uses sort of the magnetic field of the motor itself. And if you use two of them, it can give you like absolute position. But the cheap kind that you can get will be basically a disc with holes in it and a LED flashing through it. That'll just give you basically speed. It won't really give you position. You'll have to integrate that for position. All right, let's talk about operating systems. I thought this would be a good topic since it's a good bucket in which to capture a lot of sort of topics that have been coming up for us, and I think we are all interested in. So just to recap, I think this is our own consensus in here on robot operating systems. So when you say operating system, a lot of people immediately talk of things like subsumption architecture, but that's not what I'm talking about. Those I think of as like architectural philosophies, not really operating systems. So operating system is something like the Plexil thing that Eric talked about on his first presentation, which NASA rovers use. But that's like a bespoke, weird thing. Then you've got ROS, and Victor talked about it on February 22nd, and then Rhett talked about it in August. But the impression I got from both their talks is it's not really an operating system. It calls itself an operating system, but it's basically middleware that does some sort of messaging, publish, subscribe architecture. And it basically avoids the hardest problem of robotics, which is actually handling the real-time coordination. So even though it calls itself an OS, I don't think ROS is an OS, at least not ROS 1. And ROS 2, it seems to be trying a little bit but from everything I've heard, it's kind of like failing. So I would not count ROS as actually a robot operating system in the sense I think people would expect if you just use the phrase. ROS is not what they would expect to see. The only other major attempt I know of is Microsoft had a thing called the Concurrency and Coordination Runtime, CCR. It was, this was when they were trying to get into IoT and robotics for a few years, and it was some good stuff, but they abandoned it in 2012. And there seems to be a general problem with computer science and software companies trying to do robotics. They approach it as like a computer science problem with slightly more complex peripherals, which I think is the wrong direction entirely to do robotics. But yeah, that's one. I'm sure there's others. But my sense is the state of the art sucks. Like I said, probably because it's computer scientists trying to like do disembodied OSS plus as opposed to like starting with what a robot is and working bottom up from that. And this is why, like, when I was working in this stuff like 25 years ago, we were talking motion planning and SLAM, and here we are in 2021, we're still talking motion planning and SLAM. And people, when I was doing that research in 1998 to 2003, my professors were telling me, yeah, when they were grad students, they were still doing motion planning and SLAM. It's like, can we move on? Like, when would we say motion planning is solved, right? And I think part of there's good reasons for that, but I think if we actually had a robot operating system, that wouldn't happen. That might be a passing test for a good robot operating system.
Can I ask
Yeah.
Two questions? Question number one is, when you talk about real-time control, it appears that different robots have different needs. So a robot that tries to pick flies out of the air with chopsticks needs to be very real-time, but a robot that's on Mars, like Curiosity, doesn't need that much real-time. So there seems to be
I'm getting to
different
that. So I'm trying to
Okay.
capture all our past discussions, and you brought up this point a couple of times before, and I have captured it.
Okay,
But
different question.
Yep.
What operating system do Boston Dynamics use? They have several different robots. I'm assuming they have some type of operating
I have a
system.
guess. I have a guess about pieces of it, but I haven't. I did some Googling. I couldn't figure it out, but I have a guess on how they do a few parts of it, which also I'll talk about here. Okay, so some of these things.
Sorry,
yeah.
a quick note, because on your previous slide, Plexil is not really an operating system. Okay, it's a planning environment. Okay, so in that sense, it's more like a middleware for robot movement planning on top of some operating system that they are using at NASA. So in that sense, Plexil is more like ROS, basically. Okay, so it has the same issues.
Oh, okay.
It's just a clarification, because when I presented it, I was presenting so back February. Okay, I was presenting in the framework of a full stack, okay, of things we will need to approach from the software perspective, and that include the operating system. And so I presented Plexil in that context, and so maybe it was a conflation. And if some people believe the Plexil is an operating system, so it's not. It has to run on some operating system.
Got it. And I'm using the term loosely. Like, even if we, get to what I would consider a true robot operating system, it might actually run on top of Linux or underneath Linux or something like that. And it might also have like a traditional OS running adjacent to it somehow. So I'm kind of keeping the definition loose now. So I think the way you describe Plexil right now, I think it still falls within the loose category of what I would consider in the ballpark of an operating system.
All right, thank you.
All right. Let's see. Okay. Did I? Sorry. Okay. So I tried to I don't know, reflect on the discussions we've had for the last year and try and capture some top level principles of what we might desire in a true robot operating system. Some sort of, it's like a feature shopping list. So my big one is you have to start bottom up from the demands of real time, real space, real matter. So I'll talk about what I mean by that in a bit. I want situatedness as a first class concept. This is not an abstract thing that's living in nowhere. It's something that's sitting somewhere. So situatedness in an environment is a first class concept. Embodiment is also a first class concept, as in it's not like a brain in the cloud, it is a brain in a body. So, and we want that to be a strong idea. So that's point number 4, which is the brains are not like arbitrarily related to the bodies, as in it's not like the brain can be uploaded to the cloud and then downloaded onto an entirely different robot and it'll work. So if that happens, then something is wrong. And so I'm trying to treat that bug as a feature. So I kind of believe that a sound robotic operating system will actually have strong coupling between mind and body, basically, so non-dualistic. So it should not be possible to upload a rover operating system into the cloud and then download it into like a fly catching chopstick robot and have it work easily. There should be some strong coupling between the two kinds of robots, and that should have effects. That's what I mean by properly embodied.
I didn't quite understand the difference between number 3 and number 4.
So
What is-
embodiment says that the brain is inside a body. Non-dualistic means the brain and body are kind of one. You shouldn't artificially separate them. Does that make sense?
No.
I might have.
What does it mean? What's the distinction? How could something do number 3 and not do number 4?
It could, for example, if it's a brain that has mental models of the world around it and does everything completely sort of in mental models and simulation and then sends imperative commands to the hardware, that's a more dualistic way. Whereas a robot that does computation, for example, by arranging pebbles in the environment, that's kind of like very tightly integrated into its body. So it's like, is the mind separate from the body or more tightly integrated? So Minecraft, for example, it's Turing complete as an environment, but the computation happens with like actual physical or virtual physical objects, the logic of them being, stacked and stuff.
So by embodiment, you mean interaction with the world?
Embodiment means the brain is in a body. Situatedness means the body is in the world. So situated means body is in the world. Embodiment, brain is in the body. Non-dualistic means you shouldn't make an artificial mind-body separation.
I shouldn't be able to run simulations on what happens if?
No, you can run simulations, but how do I put it? Characterizing the brain independently of the body would be kind of meaningless. Like if you took the brain out of the body and looked at it, you should be able to infer things about, hey, this is a rover brain because I can see that it's adapted to a rover body. So think of it as like coupling, basically, design coupling.
Okay.
And
I have a concrete example to illustrate the kind of problem, because I'm very much into those things, as you know. If we take a robot that has a camera, okay, like an Intel RealSense, whatever, and we take another robot with the same camera, same model and so on, okay, we can think from an abstract perspective that we have the same robot. But we know physically that two RealSense from Intel, as good as their engineering is, these two cameras are they're a little bit different. Okay, it's subtle. Okay, and this is what the number 4 means. Okay, that if we have a software that runs on a robot that has a RealSense, so it works. Okay, and when we move that software on another robot with another RealSense, it will work. Okay. But the thing is that it's because we are making a lot of simplifications. In fact, if we look fine enough, these RealSenses are slightly different. Okay? And so when we talk about using sensor data, okay, especially at a high frequency, we simplify everything, saying that statistically we have the same signal, but the signals are different. And so the non-dualistic approach to such kind of thinking is to say, okay, I don't even know anymore the difference between my RealSense 1 and my RealSense 2. Okay? And this is usually very, for me, it's very important when we think bottom up, basically, that we leave on the side less detail than we usually do in a top-down engineering.
It actually sounds to me like the opposite. In other words, it's not about non-dualistically, it's rather individuality, what you just described. What you just said is because we are embodied, number 3, we have the software has to be individually adapted, not just calibrated, but more than calibrated.
So you're kind of like jumping ahead to point number 6, because that's the basic idea of software 2.0, which is basically deep learning. And the basic idea of, so this is Andrej Karpathy's talk, which I recommend you watch if you haven't yet, but it basically says you do as little as possible in code as we normally think of it, which is software 1.0. And software 2.0 is all the intelligence embodied in the data through deep learning. So you might have an extremely small domain model learning framework that runs on a robot that runs around. So say a rover has a very minimalist program that just makes it run around and learn its own body and the environment. And then all the intelligence gets captured in the robot self model. So right now we can only do this for languages or images or something, but we can imagine in the future it can learn its whole environment. And this then would be a software 2.0 type robot operating system that's primarily in the form of a trained self model. So this is actually how humans work, right? Like you don't have a mental model in your head that says, here's how I move my hand. It's like integrated into your brain that your very specific particular hand moves in a particular way. And if you could do this thought experiment of your brain being transplanted into somebody else's body, all the deep learning and trained model would fall apart. You wouldn't actually be able to control that body because it's not that type of software. So basically, Eric's point, if you take it to its logical extreme, you get deep learning as a way of like programming robots, which is point number 6. I think we should actually want that. We should want a robot operating system that supports this software 2.0 deep learning way as its primary programming paradigm. And you only fall back on 1.0 if you have to. All right, quickly go through the other points since I have some examples on what I mean by all this. Robot OS must balance essential identity and socially constructed identity. This is a point I actually borrowed from political science. So physically, what I mean is I have my rover, you have your spider bot, and we think of them in a very common sense way as 2 different rovers. But if we succeed in doing what you're talking about, which is you can borrow some capabilities on my robot, I can borrow on your robot, and at any given time, there may be actually synthetic virtual robots that are completely different. There may be like 3 synthetic robots using the hardware capabilities and affordances of like 3 physical robots. And that's what I mean by socially constructed identities. But I think there is something essential on the physical side as well. And I think this tension kind of is present in human societies as well. Like humans, when they're super individualistic and libertarian and read, sovereign individual and go off and try to live on an island by themselves, that's one way of being human. Another way is living in a community, getting your life entangled with a bunch of other people. That's another way. And that's a tension that's present in how we kind of like create and navigate identities as humans, right? And I think something similar will end up happening for robots, and a robot OS should be able to do that. So this is probably the most complicated point. I got it from Hannah Arendt's political science ideas in the human condition. Let's see, the others are relatively straightforward. So coordination control languages, Rhett has been talking about this. You want like something that interoperates with human a little. You want to embody like things that are relevant to physical bodies, but not necessarily to like, virtual intelligences like survival, evolution, mortality. A robot can die. Computer in the cloud, if it's a software image, you can back it up, reboot it. In a sense, it's like immortal, whereas a robot in the physical world can actually die. And yeah, I think there's actually something interesting if you're able to think at the Asimov 3 laws level. Like, even though it sounds like very dated 1950s science fiction, I think it's worth revisiting Asimov 3 laws kind of thinking at a robot OS level. Like, what could it mean? So this is my quick list of 10. Some of them are my own idiosyncratic ideas. Some of it came out of our discussions.
And I want to ask about number 10.
Okay.
You're basically requiring a very deep understanding of the world.
Probably. So I don't mean the specific 3 laws that Asimov proposed, but I mean things at that philosophical level. Yeah.
The level is that I can identify more important objects and that I can understand that something bad is about to happen to them, some type of prediction. And I also have to have judgment that it's bad and not just happening.
Yeah. So you're assuming a lot. So I think a robot OS should sort of prepare for being able to do that kind of software. So the OS doesn't need to do all that, but it should sort of natively have that possibility engineered into its possibility space.
Have you given any thought to how these bullet points interact with each other or not? In other words, you can have 2 bullet points that work together, and you can have two, the one requires the other, and you can also
I
have
haven't yet.
tools that have no
I threw this
connection between
list
them.
together earlier today, so it's gotten about 10 minutes of like conscious thoughts, even though of course I've been thinking about it for a long time, but 10 minutes of conscious thoughts. So definitely that's something we should do. We should sort of continue to collectively refine this list and figure out the interrelations and stuff.
Mhm.
Okay, so obviously some of the interrelations come out as implications. So for example, if we were to do an OS project, I think it would naturally end up happening that it works better in rover robots and worse in other robots. So this is sort of an implication of some of the principles. Another one related to that software 2.0, there was this paper that came out called PonderNet, and it argues that, so you guys are familiar with Daniel Kahneman's System 1 and System 2 brain architecture, right? It's kind of like made up, it's not really neurologically meaningful, but the basic idea is System 1 is intuitive associative thinking, and System 2 is logical, deductive, kind of analytical reasoning. And his whole book of like thinking fast and slow is based on that. And this paper, basically one way to, I've linked the tweet there, but somebody tweeted that there's no such thing as System 2. System 2 is simply System 1 running slowly. So the implication is everything is software 1.0, which means associative and intuitive, which means our previous item number 6, software 2.0 as primary programming paradigm means do everything with deep learning. And it's almost a little bit of an admission of failure if you can't do it with deep learning, and you're forced to like go to like logical inference or like classical planning or something. So it's a sort of aesthetic bias almost in how you approach the problem space.
I just want to comment that it doesn't have to be deep learning. It can be other types of goal-directed programming. That's all.
So I think I'm using the term software 1.0 and 2.0 in a very specific way that Karpathy defines.
Yeah.
We should, I think anything that maps to that divide will work. So maybe there's types of goal-directed reasoning that look like software 2.0, for example. Yeah.
No, goal-directed learning, not goal-directed reasoning.
Yeah, okay. Yeah. Basically, if it's smart code and a lot of smart code and a scarcity of dumb data, it's software 1.0. And if it's a small amount of dumb code and like a vast amount of like data, it's software 2.0. That's the rough distinction Karpathy makes. Like, it's like the, have you guys seen the Google paper that came out in 2008? It was called The Unreasonable Effectiveness of Data. That was one of the papers that kicked off the machine learning revolution. But the basic claim was simple algorithms with a lot of data beats complex algorithms with a limited amount of data in every sufficiently large scale application. Okay, so this slide is just my attempt based on weak recall of ideas that have come up in the last year. So abductive reasoning, I think, fits in naturally with OS level thinking. Rovers in a containerized VPNized society, I think, fits in sort of for a robot society. What you've been working on, Meyer, borrow and lend capabilities fits in. The affordances idea that Anuraj was talking about a few weeks back. My basic design interest in like scavenging parts from each other and being able to like repair yourself with like crap you find in the junkyard. Rhett has been talking about languages for representation and understanding. And obviously, as we continue to do this, lots more ideas will fall into this OS level bucket. But to put it all together into something that looks like an OS, we kind of need more of like a philosophical true north. So I was trying to identify some of that. Sorry, hold on just a second. So I was looking back on my last experience doing this stuff around 2006, which interestingly was just before deep learning and all these things broke out. And I think Eric's experience is kind of similar. We have a lot of overlap. And I was trying to map them to similar ideas or similar buckets of ideas that are now in fashion and like how have things changed. So for my postdoc, I used a lot of those things in the red on the left. So a way to do qualitative spatial reasoning called region collection calculus. Today, if you wanted to do that, you would necessarily integrate that with like deep learning, CNNs, things like that. So that's one transition, and how you do spatial representation and reasoning has changed. I used something called temporal interval calculus, and now I'm working for my book on something I'm calling a temporality stack. So thinking about time has changed. So there's a whole bunch here, and roughly it's one-to-one correspondence. So each idea on the left is a 2006 vintage idea. On the right is something roughly in the same bucket. So I'll talk about a few in a little bit more detail, but a couple of interesting ones that some of you may not have heard of. One of my favorite ideas is, this thing called Pebble Automata. So this was some interesting robotics research in the 60s, where people asked, how simple can a robot be to navigate a maze? And they were using a particular kind of like memoryless state machine that was called a Pebble Automaton. It was not memoryless, perfectly memoryless, but it had like a Hansel and Gretel type memory mechanism where it would carry a bunch of pebbles. And the idea was you navigate the maze and you drop a pebble anywhere you like. And the basic theoretical question was, how many pebbles do you need to navigate a maze? And people did a bunch of research showing like, 5 pebbles were enough, blah, blah, blah. And eventually somebody showed that you can solve any arbitrary maze with just 2 pebbles. If you can pick up and drop 2 pebbles, you can solve a maze. So that's, by the way, an example of like a embodied, situated, and non-dualistic way of doing computation, where the nature of the body and the nature of the environment are so entangled, there's no meaningful sense in which you can take the brain of that robot and put it in the cloud, because it's like embodied in the environment and the body. So that was Pebble Automata. And if I look today and you look at all the kids doing like wonderful things on Minecraft, it feels like that approach to computation, where it's basically spatially embodied everywhere around you, it's becoming the norm. And it feels like we should, if we do a robot OS, it should think like that somehow. So I just wanted to point that one out. All right, few interesting ones that I was using in my postdoc research that I think some of you may like. So there was this whole field called qualitative spatial reasoning, and it was about how do you do reasoning in space without worrying about X, Y coordinates and path planning and stuff. And it uses this topological sort of scheme of how can 2 regions be in relations to each other. So turns out you can build a formal system based on just 8 primitive relations. So 2 regions can be completely disconnected. They can be touching, they can be slightly overlapping. One can be inside the other, or one can be enveloping the other and touching on the inside. They can be exactly equal if they happen to be geometrically equal, or one can be completely included in the other. And it turns out, for those of you who've done some topology and math, this maps to a T3 space in topology. So you can like formalize and axiomatize this extremely well. You can do reasoning with this really well. And this is a primitive of 8 primitives. And you can do something similar with time. And in time, you get 13 primitive relationships because there's an asymmetry in time between before and after. So again, think of 2 intervals that are of different lengths and ask how they can be in relation to each other. One can be before the other, one can end just when the other begins. They can slightly overlap, they can start at the same time, they can end at the same time, or one can be exactly inside the other. And this becomes kind of very useful in robotics when you have to do coordination, where the precision has to be relative, but you don't care about the numbers. So for example, if you and I want to lift a table together, it's very important that we both lift at the same time. Otherwise, it'll get imbalanced and we might stumble. But it doesn't actually matter that we lift at t equal to 3.5 seconds, right? Which is why humans have a very rough coordination system that says 1, 2, 3, lift. And we get very precise coordination, but we don't actually care about the absolute time. Similarly, if you have like a weird door lock where you have to hold down a handle and twist another knob at the same time, it's like while you're holding down the handle, the knob has to be twisted. So one interval of time has to envelope the other, but the precise boundaries don't matter. This particular example was used in one of the DARPA grant challenges for the search and rescue robots, where a robot has to be able to get into a building and open doors. So this is the kind of problem that humans solve intuitively. We like fiddle around with knobs and figure out that, yeah, you hold the handle down and turn this other thing and it opens. and we don't do like precise time computations. So this is a way to do qualitative temporal reasoning. I think this is a very useful foundational building block for an OS. Third idea that I used is something called a maneuver automata. And this is kind of I think one of the best examples of collaboration between controls people, AI people, and pure computer science people. So the way this works is, typically when a computer scientist solves a robotics problem, they do something like, all right, the robot is going to move on a Manhattan grid. It's going to move like on a chessboard, right? And they ignore all the dynamics, and you get very inefficient and sometimes impossible motions. Like you can't do that with an airplane. It has to be dynamically stable. And if you try to move it on a Manhattan grid, it's going to crash. But on the other hand, if you do it the control theory way, which is model the physical dynamics, build feedback control loops, check the stability criteria, all that, you get a stable thing, but then it doesn't generalize or abstract very well. And what the maneuver automata people did was they came up with a way to very systematically do both at once. And this is, the math is very complex. The way this works is, if you take an airplane, there are things called trim trajectories. So flying straight in a straight line, you can indefinitely do that in a stable way. On the other hand, if you're doing something like a barrel roll is moving the ailerons in a particular way for a specific period of time. It'll flip over in a complicated way. It's a maneuver, right? It's a finite time, unstable maneuver. And the way this theory works is you go from one point in a stable manifold to another point using unstable trajectories. And that basic idea is called a maneuver automaton. And the interesting thing is the high abstract level can be handled with like math that looks basically like finite state machines or like computer science stuff, but the low level stuff can be extremely sophisticated dynamic control algorithms. And this is, by the way, you were asking about Boston Dynamics before. Looking at how the robots work, I'm 99% sure they're using maneuver automata. And this stuff has been around since like the early 2000s. It was at MIT. Emilio Frazzoli and Eric Ferron did most of the work. But one of the first things they did was a helicopter. So they had a human pilot basically fly a helicopter manually, doing all sorts of acrobatics, like barrel rolls, flips, all kinds of things that humans know how to do. And then they encoded it as a maneuver automaton, like just recorded everything the human was doing, parsed it as a language of control, and then discovered that it has like a vocabulary of so many unstable maneuvers and trim trajectories. And then they modeled it as a maneuver automaton. And this turns out to be an extremely successful way to do fairly complex agile robotics. So people in the AI, deep learning, pure computer science world somehow don't seem to be aware of this. Like I keep seeing like robotics done by CS people that looks kind of dumb when you could do this. So that's why I'm pointing this out. But everybody in like hardcore robotics and control theory knows about this now. It's like well-established techniques. Modal logics. So this was another thing I used. So you guys are probably familiar with basic first order logic. So the second row over here, it's logic done with statements with universal and existential qualifiers, right? So for all x, fx is true. So that would be that upside down A qualifier on a statement. And that reverse E is there exists a path in this world that goes from point A to point B. So this is like universal and existentially qualified logic. That's called a first order logic. If you add a second order to it, you get something called a modal logic. And it has these two operators, which are basically generalizations of universal and existential qualifiers. So this little square symbol means in all possible worlds, something is true. And the little diamond symbol means there exists a possible world in which something is true. So for a robot example, it could be that your battery is dying out, you have various mission criteria, and there's no way to save yourself, and you realize in all possible worlds, the rover is going to die, right? So that's an example of like a all possible worlds modal statement. Whereas if you have enough battery to get home to the base station, but only if you very optimally go on a few routes, then you'll live, otherwise you'll die, then you might say in one possible world, the robot lives by going home to the base station. So again, this is computationally interactable. Obviously, it's not going to be as simple as like strips planning or something. I don't know of any strong reasoning engines that can do modal logic, but people have tried like very rudimentary things. but I think a good robot operating system has to do modal logic. And you can do this with multi-robot systems as well. They can argue with each other. Like if I'm saying something like, if my robot goes from point A to point B, will you go from point C to point D so we can coordinate some activity? So we are doing subjunctive logic reasoning where we are talking about possible worlds where you and I do completely different things. And you argue about that. You use that as a basis for debate. And humans do this very naturally. And there's a lot of work on this in a field called dynamic semantics. So there's a lot of work here. And I think something like this will be needed for multi-robot coordination.
So I have a quick doubt here. The temporal logic and this modal logic, everything seems to fall under a system 2 type of thing, right? Like instead of, and the more we add these things to the stack, wouldn't that be contradictory to the one we were talking about in where we use software 2.0 as the, what is it, primary means of programming whatever the bot is doing?
So that's the reason for this slide. So I think one of the big cultural shifts that's happened between when I was doing my postdoc and today is all these ideas have gotten reinvented in ways that emphasize a software 2.0 approach. And the challenge is if you find something useful in the left column, can you update it to work within a software 2.0 paradigm? So the region connection calculus I told you about, that's a very formal axiomatic way of reasoning about space. CNN. So vision, on the other hand, it looks at arbitrary images and says there's a cat in the picture, right? Can you somehow do things like the cat ate the food? So in region connection calculus, you would say the food pellet went inside the spatial region represented by the cat, right? So it would be a very formal kind of statement. But can you capture that kind of logic with software 2.0 approach? What's another good one? Maneuver automata. That's like formal computer science logic. But OODA loops, I think, are a very intuitive learning paradigm that have many similar characteristics that maybe will work. But these are all like open questions. I'm posing this as a challenge, not as solutions. But yeah, I'm just listing some of the ideas I used in 2006 that I thought were very fertile, and it would be nice to put them in a OS somehow.
Again, I have 2 comments. The first one is that I just realized that your list of requirements for an OS didn't include anything social.
It doesn't? It does.
No? No.
Society of mind is a fundamentally social idea.
No, not this list. The list of 10 points on opinionated vast
Oh,
system.
okay. Did I not have anything?
At the bottom, maybe number
8 and number 7. So 7 and 8 are social.
Yeah, but it doesn't mean they can talk to people. Number 7 says it believes about itself, but not that it needs to be able to coordinate, have arguments. It's very interesting. I can have an argument between rovers. Okay, that is a basic operating system capability.
Yeah, so I would say that's a level of commitment that's at the programming language design level rather than OS level. So the OS should be open to letting that happen. But maybe some robot systems argue with each other. Some robot systems never argue. And it's like a beehive where the queen bee tells everybody to do everything.
Yeah, but the OS level components are, 1, persuadability. The rover has to be able to be persuaded. And the other one is that it has or not, I don't know, some sort of model of other rovers. That's a basic capability, the same way that you have theory of mind of yourself, you have theory of mind of other rovers.
So I think I agree with you, and maybe the language I've used in this list of 10 isn't very clear, but in my mind, it's, so there's a theory of mind problem right here, but in my mind, it's actually captured in 7 and 8. So, but the language could probably be improved and like make it clearer that that's somewhere in there.
Okay, so my second point has to do with your list of 12 items. I just want to comment that this is part of a curriculum for our summer winter school. Okay, when you say this is something that a lot of CS people don't know about robotics, and that is something that they don't know, and here's an architecture which is widely used. When you make those statements, to me it says, oh, this should be in the curriculum we want to suggest.
Yeah, I'm sure there's like lots of ideas between fields that if we can identify the right set of ideas and sort of put them in a school format, something interesting should come out of it. Like,
but
yeah.
We're not as rigorous as a school. We don't have a fixed curriculum. It's more like a seminar level.
Yeah.
So we have these different ideas that floating around, and catch one and eat it.
Yep.
I don't know about others, but I seem to be more familiar with the things on the right and less familiar on the things on the left.
That I think says basically the difference in our ages. I think, when did you go to grad school?
From 2010 to 2015 or something like that.
So I think the paradigm shift I'm implicitly sort of gesturing at here happened sometime between 2006 and 2010. Like lots of things changed quite dramatically. And I see Eric nodding a little bit because I think several of us have noticed it. It's like many things shifted from the left column paradigm to the right column paradigm, and people who got their training even 2 years apart ended up having very different mindsets based on like what ideas were popular and stuff. Like deep learning was not a thing. Yeah.
I confirm that deep learning is from 1991, basically, to be okay. And the thing is that until 2010, I have a PhD in AI, okay, for whatever that means, okay. But until 2010, when I was telling people that I graduated in AI, they would tell me, "Oh, you're working on making games," okay. That was the feedback I had, okay, all the time, okay. So for a long time, okay, say until recently, okay, I would say that I was basically a software engineer or a computer scientist or whatever, okay. But I stopped talking about AI because I was not. I think games are great, okay, but it's just that that was the thing. And exactly as Venkat has pointed out, is around the late 2000, okay, around 2010. It was really a paradigm shift, okay. And so I'm not surprised by the comment, okay, from Anuraj. And unsurprisingly, I know much more on the left, although now pretty advanced on the right as well, okay. But on the right, it's my knowledge is either from the 90s or from the past 10 years, basically. It's a new world in many ways, at least for old people like me.
Yeah, and you're right. Like some of the core stuff on deep learning, even though it was done in the 1990s, the computers became powerful enough to do useful things with them only in the paradigm shift time around 2008 to 10. So suddenly a lot of things were started being done very differently. Let's see, where was I? I'm just going to flash it, not talk about it. But if you're on my mailing list, and by the way, anybody who wants like a free comp subscription, if you're not on the list, I'll give it to you. But yeah, my book on time, I'm using the stack model of time, 7-layer, which is explicitly inspired by operating system stack diagrams or networking stack diagrams. So this is how I'm thinking about time. And I think it's actually a good blueprint for heavily time-centric operating system. So an operating system that lives in time as opposed to like, time being just a clock measurement. Okay, so just, I don't know how we are on time, but if people are interested, I can quickly show you guys where I was in 2006 when I last looked at this stuff. I just found my old presentation from then. If you're interested, I'll spend a few minutes.
Windows XP.
Hmm?
Windows XP, right?
Yeah. Is it? Yeah, it's Windows XP. But this is basically, I built a proof of concept, I guess, a shell level operating system for multi-robot coordination using some of the ideas I mentioned. So on the top left pane, you can see a region connection calculus based representation of an environment. So you have lots of regions that can overlap and robots moving around. On the right, you have basically a temporal interval calculus based representation of a stream of events. And on the bottom left, actually, I have no idea what that's another temporal view. So that's the quantitative temporal view as opposed to the qualitative temporal view. So the reason I wanted to flash this is you can actually go from that set of concepts to actually building something that is about multiple robot systems and so forth. I wanted to leave this quote up in the as a closing thought. So this is because ADA was initially planned for defense applications, and if your program is running on a missile that's going to blow up on impact, you kind of don't need safe termination procedures. Yeah. It is kind of late, so I won't try to talk about my old slides, but if there's interest, I can do another session and talk about what I did back then.
Yeah, it would be
That'd be great.
interesting to know about the temporal interval calculus and all the other things, how they play with each other and how they interact with the robotic system and stuff like that.
So maybe what I'll do is I'll try and like rework my old slides into more of a summer school format for basically old people pre-paradigm shift ways of doing, thinking about this stuff. So that might be a fun mix of both history and old paradigm introduction. Okay, so that's my progress report and AIOS. And I'm hoping there's enough interest in all this that maybe we can actually try to build one. Robotic OS.
What do you suggest? Are you suggesting building a robotic OS as a group goal for the next year? Is that what you're doing?
Possibly, or pieces of one, or a specification for one. And
that's what I mean, but
yeah,
that like a group goal.
Yeah.
So how would we work together?
I have no idea. This was like just a thought starter. I threw whatever initial thoughts I had on the slides, and yeah.
I'm asking the people on the top of my screen.
I think somebody gets dragged into putting some scaffolding down for a white paper.
And so just one thing, on the slide where you put 10 points, okay, the thing that for me, okay, there is a very close mapping to the last presentation I've made, okay, when I talk about so abductive reasoning, but abductive reasoning is toward the end, okay. Before that, it's about, I talked several times about the soup of data, and we have to make, a robot has to make sense about the soup of data. And these are basically the 4 or 5 first points you put on the slide, okay. And so, in one sense, that can be maybe the base for a white paper. So actually, I've never seen it that way. Thank you, Joshua. And I may just be doing that. But also in 2 weeks, it will be my turn to present. And what I'm going to present are early results that are actually covering point 2, 3, and 4. Okay.
Nice.
So yesterday we had a quick call with Meyer to see the first version. Okay. I will try to advance it to the level to see where that is going. Okay. But for me, the music is on, and I'm on it. Huh? I love it.
Yeah. And I think this group has just the right mix of experiences and working on the right variety of robots that something interesting could come of what we're doing. And honestly, like if you look around in academia and industry, for even though they have vastly more resources and like depth and history on this stuff, for some reason, this particular problem seems to have fallen through the cracks. And like, despite multiple attempts, like nobody's actually tackled this head on and like asked, why isn't there a good robotic operating system? Maybe the answer is because there's like fundamental problems we haven't spotted yet. But if so, it would be a nice outcome if we even identify the fundamental problems of 10 reasons why robot operating systems are impossible. That would be a nice result.
I just have to comment, we're not talking about robotics operating systems. We're talking about rover operating systems.
Rover, yeah.
That makes a problem easier.
Yep.
Will anybody here be attending ROSCON on Wednesday and Thursday.
I didn't know that was a thing. Yeah. Is that online, virtual, and free?
I believe it's free.
That's what.
Yeah, I'll be attending a in-person viewing party on Wednesday here on the East Bay in Oakland. But yeah, that is occurring this week.
Would you have a link? Because one of my partners has joined the one here in Tokyo, and apparently it was pretty good. Do you have a link to that one?
Yeah, let me.
It's roscon.ros.org, looks like.
Oh, thank you.
There's also the NVIDIA conference.
Yeah, people who go to these things should, I don't know, give us all updates or like informal trip reports, since we can't all go to all of them.
Yeah, my colleague is going to be giving a talk there, and so I'll be watching that and talking to the people. So I could give a little summary the next call.
About next week, I will be traveling. I think Rhett had volunteered to change his time. What was it? I can
Okay, so
do
next
on
week is,
November 1st.
Rhett?
Yeah, we swapped.
Okay.
That makes me.
But something's changed. I can do it on November 1st. But right now it says it's Eric.
Okay, I'm stopping the recording.